Hello and welcome to my video, lesson 1.3, Unions and Intersections of Sets. Alright, we're going to be looking at a bunch of different notations for sets, which is kind of funny because in 1.1 we talked about set notations, but here there are some more, and they're the more specific ones, I suppose, where they mean something very carefully. And so we're going to be highlighting what they mean one at a time. So our first one here is A intersection B. So this little symbol here is an N, and so there's an intersection, there's an N in intersection. So that's how I try to remember this. It's also in the middle. It's inside of our Venn diagram. So it's everything that is covered by both A and B. This is the key phrase here. It's both A and B. All right. So if they are two sets that aren't touching, they're disjoint, then they have no intersection. The intersection of them would have a empty set. So just be aware of that. Or if they are fully enclosed, a subset, A is a proper subset of B, then A would actually be, like all of A would be the intersection. So just be aware, whatever overlaps, that overlap is in both A and B. That is our intersection. If we're talking about the union of A and B, it means something slightly different. The union uses a little U symbol. It's not really a U when you type it in. It is a special symbol, but it looks very much like a capital U. And so this symbol is a union, which means that it is in A or B or both. So there's an or statement here. It's in any of it. Any and all of A and B. So that would be this part. Let me just show you here. Everything inside any of the two Venn diagrams would be in A or B or both. All right. Here's another symbol we have, which is A minus B. We use a backslash for this so that we aren't dividing by accident. It is a different meaning here. We're including everything in A, but not in B. This is basically the second half here, not in B. So it's a backslash. So everything in A, okay, but not in B. So it doesn't include the intersection. All right. Consider the following set of multiples of 3 and 4. So if you just consider a set that I'm going to label right now. So that it already has a T. T for 3 and F for 4. Okay, so multiples of 3 and 4. And I guess maybe I should have drawn it. But I'm going to do it up to, I don't know, 16 or something. So multiples of 3. So we have 3, 6, 9, 12 is common. 15, 18, 21, and then 24 is common. How about I stick with this set of numbers? So 4, 8, 12 is common, 16, 20, and 24 is common. Let's just stick with that. Okay, so this is a set of multiples of 3 and 4. Okay, with this set, find the following. So basically you're trying to find, based off of what we've already looked at, find the following underneath here. So T, or the set of multiples of 3, minus the set of 4. So what part of our Venn diagram would this be? Well, it would be our 3, 6, 9, 15, 18, 21 part. And then the n symbol here tells us we need to count that. So 1, 2, 3, 4, 5, 6. There are 6 items in that set. All right. Next, we have the U symbol for union. So that includes everything inside both sets. This will take a little while, but 3, 4, I guess I could draw that properly. 3, 4, 6, 8, 9, 12, 15, 16, 18, 20, 21, 24, and that is that set. Whoopsies, I'm not drawing my squiggly brackets properly. There you go, good enough. And now we have to count them. 3, 6, 9, 12 items in that set. Okay, the intersection of both sets includes the two numbers 12 and 24. Excuse me. Okay, if we count that, there's 2 of those. Oh, I guess I should use a different color for that. Let's go with blue. So 12 and 24. There's 2 numbers in there. Okay, and then our last one is the union, but not including the intersection. So still going to take a little while, but basically 3, 4, 6, 8, 9, not 12, 15, 16, 18, 20, 21, not 24. Whoops, I guess I can finish that like this. Not 24. So it is 10 is the number in between. Alright, so that was pretty complicated to get there, but hopefully this makes a little bit of sense, because those, basically number 4 is kind of the most complicated that it could get to. Alright. Consider the set of 40 athletes. I'm going to just zoom out so we can actually see the entire question, or perhaps I can just... Yeah, I can. Okay, consider the set of 40 athletes. 16 swim, 34 do track and field. If everyone surveyed does at least one of the two, that means swimming or track and field, how many do both? So this is a little bit of a little word problem, tricky word problem. So swimming, track, and field. Okay. Everyone surveyed does at least one of the two. There are 40 in total. 16 swim and 34 do track and field. Now the trick part here is that we can't just write down 16 or 34 or 40. None of those actually fit into our Venn diagram. The total of all 3 numbers need to add up to 40. And 16 includes everything in this entire circle, including the intersection. 34 includes everything in this circle, including the intersection. So what we have to do is add 34 plus 16, see what that gets us. That gets us 50 on the nose. And we know that there should be 40 athletes, but we currently have 50, so we obviously can't just have those numbers. If we add some in the intersection, every one that we add only counts as 1 instead of counting twice. So if we put 10 in the intersection, minus 10, that would give us 40. So let's start with that and see if it works. So 10 in the intersection. Now what we can do is count how many more we need to have. So 6 more to get to 16 for the swimmers, and 24 more to get to the 34 for track and field. This means that we have 34, 16, so that's all good. And those three numbers, 6 plus 10 plus 24, should add up to, and they do add up to, 40. All right. This is the logic way of going about solving this, but there is actually a general formula for this now, where the union of both, that would be count up all the different people in both, so that would be 40, equals the sum of A, which is, let's say, 16, plus the sum of B, which is 24, minus the intersection of both, right? So the intersection of both is the 10. Okay, so we actually did, whoops, not 24, 34. I'm like, why is that not adding up? So we actually did that up here, but we talked it through, right? So by doing that, we can actually figure out what the intersection should be. So this is the intersection. We don't know the intersection in this question, so we actually just have to solve for the intersection. So that would mean we could do opposite operators to move that across to the other side, and opposite operators to subtract by the 40, and that's how you get the 10. So this would be our principle of inclusion and exclusion, using the formula method to get the same answer of 10. Or, I guess not from there, over yonder. Alrighty. I hope this video helps you understand these different symbols, I suppose, and what they all mean, the unions and the intersection of sets. Good luck.